Another Day, Another Story. A Brief History of Time, Part 9. Certainly. Here are the topics covered in Chapter 8, The Origin and the Fate of the Universe, by Stephen Hawking, presented with subsection numbering. 8.1. Quantum Effects and Early Universe. 8.2. Influence of Religion and Personal Perspective. 8.3. Early Universe and Hot Big Bang Model. 8.4. Formation of Elements and Early Universe Stages. 8.5. Universe's Continued Expansion and Cooling. 8.6. Formation and Life of Stars. 8.7. Stellar Evolution and Element Formation. 8.8. Early Universe and Evolution of Life. 8.9. Unanswered Questions and Initial Conditions. 8.10. God's Role and the Anthropomorphic Principle. 8.11. Inflationary Universe Model. 8.12. Criticisms and Resolution of Flaws. 8.13. Introduction and Background. 8.14. Inflationary Models. 8.15. Initial Configurations and Weak Anthropic Principle. 8.16. Quantum Theory of Gravity and Imaginary Time. 8.17. No Boundary Proposal and Quantum State of the Universe. 8.18. Implications and Conclusions. Please note that the content within each section may vary in length and depth, but these headings should give you an overview of the topics covered Chapter 8 of the book. Chapter 8. The Origin and the Fate of the Universe. 8.1. Quantum Effects and Early Universe. Einstein's theory predicts the universe's beginning and potential end. Quantum effects might cause black hole evaporation. Could quantum mechanics similarly impact the Big Bang and Big Crunch? What happens during early or late universe stages with strong gravity? Does the universe truly possess a distinct beginning or end? 8.2. Influence of Religion and Personal Perspective. Rekindled interest in cosmology at a Vatican conference. The Pope advises against studying the Big Bang as a moment of creation. Author's contemplation of a boundary-less, beginning-less universe. The author's relief at the Pope's lack of awareness about the talk's subject. 8.3. Early Universe and Hot Big Bang Model. Description of the Hot Big Bang Model, for understanding the universe's history. Universe's expansion leads to cooling of matter and radiation. At high temperatures, particles avoid clustering due to extreme speed. As universe cools, particles clump together due to attractive forces. The universe begins infinitely hot and small at the moment of the Big Bang. 8.4. Formation of Elements and Early Universe Stages. After the Big Bang, the universe cools rapidly. Universe mainly consists of photons, electrons, neutrinos, protons. Electron-anti-electron annihilation and persistence of neutrinos. Formation of helium, lithium, and other elements through particle interactions. Theoretical predictions by alpha, beta, and gamma match observed proportions. 8.5. Universe's Continued Expansion and Cooling. Universe continues to expand and cool over 1 million years. Electrons and nuclei combine to form atoms. Denser regions experience slower expansion due to gravity. Possibility of regions recollapsing and forming rotating galaxies. Formation of disk-like and elliptical galaxies depending on rotation. 8.6. Formation and Life of Stars. Gas in galaxies contracts and heats up, starting nuclear fusion reactions. Conversion of hydrogen into helium. Stars emit heat and light. More massive stars burn hydrogen rapidly, may collapse into neutron stars or black holes. Supernovas mark the end of massive stars, scattering heavier elements. Supernovas contribute material for next generation of stars and planets. 8.7. Stellar Evolution and Element Formation. Heavier elements explode in supernovas, dispersing materials. Our Sun contains about 2% heavier elements from earlier supernovas. Sun's formation led to the creation of planets like Earth. Within a few hours of the Big Bang, production of helium and elements ceases. Universe continues to expand and cool over the next million years. Electrons and nuclei combine to form atoms. Denser regions slow expansion, leading to potential recollapse. Rotation leads to formation of disk-like galaxies. Some stars explode as supernovas, scattering materials for new stars. Sun contains heavier elements from earlier supernovas. Stars' formation and evolution contribute to elements in the universe. 8.8 Early universe and evolution of life. Earth's initial conditions: hot and without an atmosphere. Cooling, acquiring an atmosphere, but initially uninhabitable due to poisonous gases. Emergence of primitive life forms in oceans through chance combinations of atoms. Evolution through reproduction, errors, and natural selection. Development of more complex, self-reproducing organisms leading to higher life forms. 8.9 Unanswered questions and initial conditions. Questions about the hot early universe, uniformity, rate of expansion, and density fluctuations. The limitations of the general theory of relativity to answer these questions. The need to consider boundary conditions and initial state of the universe. 8.10 God's role and the anthropomorphic principle. Speculations on God's role in choosing the universe's initial state. The anthropic principle as a way to explain the universe's observed state. Weak and strong versions of the anthropic principle. The role of fundamental constants and fine-tuning for the existence of life. 8.11 Inflationary universe model. Introduction of the inflationary expansion proposed by Alan Guth. Inflation causing rapid expansion and symmetry breaking. Possible explanation for the universe's uniformity and critical rate of expansion. Explanation of why there is so much matter in the universe. 8.12 Criticisms and resolution of flaws. Initial issues with the bubble formation concept. Linda's slow symmetry breaking idea and its merit. Identification of a flaw in Linda's bubble concept. Stephen Hawking's own proposal and collaboration with Ian Moss. 8.13 Introduction and background. The author returns from Moscow and heads to Philadelphia to receive a medal. The author's secretary arranges free Concorde seats, but they miss the flight due to rain. A seminar about the inflationary universe is given in Philadelphia, similar to the one in Moscow. 8.14 Inflationary models. Paul Steinhardt and Andreas Albrecht introduce a new inflationary model. This new model predicts more microwave background radiation variations than observed. Doubts arise about the possibility of a phase transition in the early universe. Lind proposes the chaotic inflationary model, using a spin-zero field with quantum fluctuations. This model explains inflation without relying on a problematic phase transition. The chaotic inflationary model aligns with observations of microwave background fluctuations. 8.15 Initial configurations and weak anthropic principle. The universe's present state results from various initial configurations. The weak anthropic principle is used to explain why the universe appears as it does. Not all initial configurations would lead to the observed universe. Consideration of a different initial state that could result in a very different universe. 8.16 Quantum theory of gravity and imaginary time. Quantum theory of gravity is needed for strong gravitational fields. Imaginary time is used in sum over history's calculations for particles. Imaginary time's mathematical nature and contrast with real numbers. Imaginary time avoids technical issues in calculations by using a different time concept. 8.17 No boundary proposal and quantum state of the universe. The no boundary proposal suggests a closed universe without singularities. Use of sum over histories and no boundary proposal to predict universe behavior. Probability calculation supports uniform expansion of the universe, matching observations. Quantum state of the universe lacks singularities in imaginary time but retains them in real time. Astronauts' fate near black holes is affected by singularities in real time. 8.18 Implications and conclusions. Speculation about whether imaginary time could be more fundamental. The nature of a scientific theory as a mathematical model for observations. The profound impact of a universe without boundaries on the concept of God's role. Reconsidering God's role in light of evolving scientific understanding. contemplation of a self-contained universe without a clear beginning or end. Thanks for watching.